in, and effectively you're going to create a table tennis ball launcher which sits in this end zone, which is 300 millimeters deep, and you have to fire 3 table tennis balls into each of these zones, A, B, and C. It's just one wave, so 3 balls into one wave, not asking you to repeat the wave. However, I would say that higher quality machines would be capable of doing it. But in terms of what's actually set out in the assignment, this is the actual specification, and you can hit these 3 zones in any order. And the details are here, and you can see that the dimensions will be approximately the size of a sort of standard table. So that's done deliberately so that if you want to practice it, or when we come to test it next year, you know, we've got you won't have to set up anything separately. It will fit on a standard desk. So then going back to the teamwork, you're in groups of 6, with the exception of 2 groups, which I'll put into 5s. And at the end of the exercise, which will be the Friday, the 30th of April, will be the hand-in. You will upload 3 things, typically. There'll be the report, there'll be some data files for manufacturing, and there'll be an Excel spreadsheet, which will contain all of this sort of ordering information. So I'll just admit a couple more students. I think that's okay. Yeah, so there are 3 things typically that each group will submit. And just to make clear, it's 1 report for the whole group. All of these are group submissions, with the exception of 1 component, which will still be in the report, and I'll talk about that in a moment. So the assessment in the assignment is broken down like this. We have an individual concept. So what we want you to do now, effectively, is go through the whole design process, in, sort of using most of what you've learned now up to this point. So there'll be a concept generation, and this will be 1 drawing from each member. And the idea is to get everyone involved, everyone putting a concept forward, and then as a group, you'll evaluate these and select which one you want to take forward for developing and designing on CAD.
Sure. Is this being recorded? Just wondering.
What I'm going to do is I'll put these files up. So I'll just go through. I'll go through. So I can set the. I haven't set the record on here, because we're going to capture all the information. It's in here. But let me just let me have a look. Yeah, let me. I'll just carry on through this. Yep. So then you've got CAD/CAM files. So I'll talk about a little bit more detail about this on the next slide. To help you with the manufacture of parts, we've actually got technician support, and they are able to manufacture certain components, typically 3D printing and laser cutting, to save a little bit of time, and then have these materials ready for you when you come back in semester 2. So effectively, the exercise is for you to design it this semester, and then throughout semester 1 of year 2, you'll actually make the prototype. But just carrying through the assessment details, the order spreadsheet, I haven't uploaded that yet. So I'm just checking suppliers and the approval of certain suppliers with the technicians, but I'll put that up there. You will actually be able to order parts from both the university and from outside suppliers. So in order for us to process all of that data, there'll be a spreadsheet that each group will be asked to complete and then upload on the hand-in day of the 30th. That will be worth 10%. the CAD/CAM files and data that you create will be worth 10%. The CAD drawings, part drawings, assembly drawings, 3D CAD model will be worth 30%. And then there'll be a 30% mark or weighting given to the report. And in the report, it will contain obviously all the information, including the drawings that you have produced in order to manufacture your prototype next academic year. So that's the breakdown of this. Let's just have a look at the overall process. So this will hopefully give you an idea as to how everything's now going to work across the 2 years. So we've got year one. So what's left of year one will be this part of the design process. And then we're going to have the summer holiday, and the manufacture and presentation of the prototype will occur in year two. So going through the design process, now what will happen is Elise will give you more details on design methods, including what a specification will actually look like. That will happen on Friday. So those lectures will help you understand this process in more detail.
Actually, Rod, can I just say, so Friday is all ready for question asking. All the materials live. I've made it live just now. So there's a recorded lecture, 58 minutes for the first one. There's some additional readings, and the slides are now available on Moodle as well. So it's a live Q&A on Friday. So it assumes that everyone should have definitely watched the first video, if not the second one as well. So they need to make time to watch the longer introduction if possible.
Okay, yeah. So thank you, Elise. So immediately after this, you'll have details posted to Moodle about the specification. And this little loop will be what we'll do after this short presentation, in the sense that what the Q&A will do is serve you well to help you know all the necessary information that you need to put into the specification. And then once you've got the specification sorted, you can then progress through and create your concept design. So this is one per team.
So, Rod, so the details for the spec that they need from you, that's not happening this Friday unless you're definitely there on Friday, right?
Well, probably what's best, Elise, if I go through this first,
okay,
and then what we could do is take the questions on this after. So just to get students through the general process, because once we've done the Q&A, I think a lot of this will make a lot more sense. But I'm just trying to give students, and trying to absorb all of this in one go is not necessarily what we're after. We're just trying to give you an introduction to now how the whole design process works. You've done elements of detailed drawing in semester one. You know how to use CAD. You've done some nice 3D isometric drawings for Andrew Event with the actuator. Now what we're getting you to do is go one step further. We've sort of given you a constrained exercise where it's a little bit open. And now what we're doing is we're effectively taking the constraints almost off completely and giving you full control so that you can generate your own concepts. You can develop them as you see fit, and then you can create your detailed design with a 3D model, your part drawings, assembly drawings, so that you would have now experienced the whole package, and that will be then finished off with the manufacture of your prototype in year two. And over the summer, what will happen is, we have 3D printers and laser cutters, and there'll be details of the materials in the resource list with regard to this, but we will have those facilities, and to help you, the technicians will manufacture these parts for you. So they'll be to your design, so they'll be bespoke parts. And then we'll also source all the components and materials that you order or put into your Excel spreadsheets, and any parts that you want us to buy out, all of that data will now come from the group. So total control is now given to the whole group. And then once we've got all that information from you, we can then make that ready for you next semester, next academic year. And then you can set about the manufacture of your prototype. And obviously I'll give you more details about that then. So this is the process that you will actually go through for design and make.
Rod, sorry, can I interrupt just really quickly? I was distracted a little bit then. Can I just double click that you clicked record? I think you said you did. I just wanted to double check.
Yeah, let me, sorry, I was just trying to find the record button.
Oh, okay.
Sorry.
Yeah, again, it's quite useful for those people in different time zones, like last time.
There we go. Yeah. Yes. This then gives students an appreciation of the whole process that we're expecting from you. And I think the nice thing is that full control is now given to the group. So let's just move on to the next slide. So as an example of concept drawing, here's a good example of an isometric for a machine that was used to unload a component. So to go in one direction, then to go in reverse, in between unloading a component. And what the student has done is put a very clear isometric drawing up so that it demonstrates the basic mechanisms by which the machine is going to operate. You'll see from the assignment that one of the conditions is that although you're going to have electric motor, your control will all be achieved by mechanical elements. And what the student has done here is, this is in effect, and you'll see this on a little video that I've got for you. This chassis is a U section, and what they've done, they've cut this away. So they've shown the hatching here. So this is very similar to what you did with the actuator when you did your quarter section. Here's the sort of the cross hatching. But what you can do is you could make that a wavy line if you like, if you want to show part of the flange here, and then show a little bit of a wavy line to make that a little bit more obvious. You can do that. But the key thing is they've allowed the markers to look inside so they can actually see the basic components of this particular prototype, how it's actually going to work. And then what they've done quite nicely is put little 2D sketches with minimal text, just explaining the reversing mechanism. And all of that fits onto an A3 sheet. It's worth 20%. So that mark is sort of rewarding students who have gone to this sort of level of detail, demonstrating the mechanics with a nice sketch, which is very easy to understand. So that's what I would say is a good example of a concept drawing. And I'll post this to Moodle so you can have a look at that. Other things that you can do, now these are optional, but once you've decided as a group which concept you want to go for, it's very likely that you might want to create a few sort of cardboard models or simple sort of mechanisms just to help you understand better how things are going to work in terms of timing. So in this particular case, what the students have done, you can see, just create some simple circular cutouts. Part of the mechanism here might be that it's a feeding mechanism and they want to get the speed of rotation well understood across the group before they proceed. So if you do things like this, then take pictures and then put them in the report. They're all valuable, even if you decide that you don't want to use them and you've made a decision to go in another direction. That's absolutely fine. You can still include things like that. And on occasion, students have actually created little foam models to see how the basic functionality will be. And again, take pictures, put that in the report. It'd be quite nice to see any design development. So in terms of other resources, so we have the resource list. So this is an Excel spreadsheet. I'll just go, you can see here, it's Excel file DM ordering form. I'll just go forward because when I load this up, this is what you'll see. and there'll be a spreadsheet with a series of tabs, and one of the tabs will be design and make resource list. And you'll see here the university will supply a whole range of materials, and there'll be costs associated with these materials. So you can arrive at a total cost for your prototype, but you'll actually put these on a form. There'll be another, you'll see here's another tab, UoB, and here will be a separate sheet on which you'll actually put the exact dimensions and quantities of parts that you actually want to order. And there'll be a series of tabs, and you'll use those tabs to define the parts and materials that you want us to purchase and cut up for you in readiness for year 2. So if I go back, so that's a little bit about the resource list. We can revisit all of this stuff. There's the machine shop, so we have lathes and mills available. There's 3D printer and laser cutter, I've already mentioned that. So there's technician support to help manufacture those parts. And then we have approved suppliers. What I'll just make clear is that you have to purchase parts from approved suppliers. Anything outside, we can't purchase for you. So this is the setup that we have. However, if you find that from the manufacturers or suppliers that we have listed, if you find that there's a part or component that you really need and it's not here, then there is a chance that we can still get it for you, but you have to check this with one of the technicians, David Wood. When you come to that point, you can just email me and I can make the link. But it is important that you do purchase things from these approved suppliers. Unfortunately, we can't get them. The university will just block it. So here's a closer list of the material. So I'll put that on Moodle so you can have a little bit more of a look on the detail prior to me posting the Excel spreadsheet. One of the approved suppliers is Technobots. There's all sorts of interesting things you can get from Technobots. There's gears, bearings, motors. So have a look at your leisure through all of that. Again, it's all available to be purchased. Here's a prototype from probably 5 or 6 years ago now. The challenge here was for groups to create a automatic seed planter. And what they had to do is create a hole in compost, then plant three seeds separately. So 3 separate holes, 3 seeds individually placed in a controlled fashion in a trough of compost. So just before I click the video, you'll see the channel that I was talking about. This sort of channel will form a chassis, and it's rigid. It's very strong because one of the issues is making sure that these sort of shafts are lined. So I always recommend, where possible, to purchase on your ordering form the channel, and then what the technicians will do is actually cut this to length for you. You can see that there's a range of gears that the students have ordered from Technobots. There's the motor, the electric motor here. There's power pack underneath. You'll see there's a belt and pulley system on the drive to the wheels, and then there's bevel gears here where they're transferring the power through 90 degrees so that they can actually activate the plunger and increment the seed into the hole. So I'll just play this, only a few seconds, just to give you an idea. Laser cut wheels, so you're free to do that. There's the plunger mechanism. These are seed placement mechanism. So it just sort of gives you an idea of the type of thing that students have produced. This is the unloading mechanism where it goes forward and back by mechanical elements, unloading, in this case, a little block of wood. But you can see here they've again, used the chassis. They've laser cut their wheels to their design, or had them laser cut to their design. So it's sort of things like this that you can do. And then the last slide, we've sort of mentioned the product design specification. The Q&A that we'll go through now will feed into that. As Elise said, she's already put a pre-recorded lecture up, so that will help you understand a little bit more about the design specification and what that will look like. And then Elise will go through typically how a design process might occur. There are different sort of models, so Elise will guide you on that. But before that can all start, what we do now is we'll open the floor up to the students for questions. And what I'll do is I'll ask you to raise your hand, and then I'll call out. I know there's a long list to scroll through, but we'll try this. And then I will give an answer. And then what Sam will do is type the question, type my answer. And this will be critical because these questions will help complete all the information that is required in order to write a product design specification. And this is a way of getting students to explore the brief from here, and then help to define with greater depth exactly what it is the group is going to produce for their prototype. And this is called a sort of double D method, but again, Lise will take you through more information on that. So
I'm using an engineering design process called from Pile and Bytes. So I'm not using the double diamond because we're just doing a step-by-step this year.
Okay, that's fine. Yeah, there are many techniques that you can use. I'll just add just a couple of words. So what will happen is I've given you the assignment here. Here it is. You're now asking questions, and you're exploring through the Q&A so that you can get greater definition, and then you can create some concepts, and you'll select one of those concepts so you can then further define the problem. And then once you've got your chosen concept, you can then develop that through those foam models, those little cardboard cutout models, so that you can actually deliver your working solution. So that's just one way of representing the process that I put up on the screen earlier across the 2 years. But there are many different models. Use the flowchart in any doubt. Use the flowchart that I've put up. That will guide you through the stages that you need to sort of to use in order to get to your final prototype.
The flowchart matches quite well with what I've done for the design lecture one.
Great. Okay, that'll be good for just reinforcing that. Now I can see that we've got Daniel Perez Thompson. So what I'll do, Daniel, you can unmute yourself and then ask a question.
Yeah, hi. I've noticed in the brief there's some ambiguity. I think it's been mentioned in the chat as well, that in one phrase it says several electric motors in plural, and then another one it just mentions one electric motor. Are we constrained on the number of motors that we can use?
Right, okay, so Sam, if you type down the question, how many electric motors can we use?
No problem.
We'll do all this live, and then the answer will be 2 motors.
So I'll ask on top of that, that's up to 2 motors, or they have to use 2 motors?
That's up to.
Okay.
Okay, thank you. And another one, sorry. Does it have to clear a net, or is that not necessary? Because I guess that determines how high the trajectory has to go.
That's a good question. So the question will be, does the ball have to clear a net? And then the answer to that will be no. But it has to clear the 700mm line.
So it can't roll It has to land in those zones.
Exactly.
And I noticed that picture, it says it has a curved trajectory, the ball. Does it need to have a curved trajectory, or can it be just a straight trajectory depending on what it's pointed at?
Right, I can see where this is leading. So the question will be, Sam, if you type, what is the trajectory or intended trajectory, if you just have a question like that. And the answer will be that it should be curved in nature. Because although I haven't put a net, in reality, there would be one. And we're proving the principle for doing that. So very good question, because it's pinpointing probably an advantage of having a sort of raised point and then firing them down.
Can I ask, so the diagram, I assume the curves are there to imply an out of page curve, right? They look like they're kind of curving to the side, you know, like you would curve a ball around a defender or something.
Yeah, that's
obviously they'll be curved due to just the trajectory nature of just the physics of firing something. But does it have to be curved, you know, to the side?
Yeah, no. So the only what that's showing with my sort of limited use of Word was that there is a curved nature to the launching of the ball. So if that, as you look at it, if you've got Y, the vertical axis, and X, the horizontal axis, then the ball is actually being fired up in Z, which is the axis coming out of the page directly at you. So that's my best effort to try and show a curve in the Z direction.
Yeah, okay, that's fine. So it is sort of a straight line firing mechanism. It's just, yeah, in the vertical trajectory, it's curved. Okay.
Yeah. So have you got 3 questions there, Sam, with answers?
Yes. Someone's asking if you could let UoB back in the call. I don't know if there's anyone who wants to be admitted.
Yeah, I've just hit admit all.
Brilliant.
Joining. Daniel, you've still got your hand up. Did you have another question?
No, that's it for now. Thank you very much.
Great. We'll go then to Dylan. You have a question?
Yeah, I was wondering if we can design it to be adjustable, or does it have to be designed such that it requires no adjustment once assembled?
So the question would be, let's say, does the machine have to be adjustable, or would you prefer the question to be, can we put adjustment in?
Like, can we design it so it's adjustable?
So if you type that, Sam, can we design it so it's adjustable? I'll leave the question as it is, because the answer is the one I hope to be asked anyway, to give, and that is that the basic control of the machine must be by mechanical methods.
Okay, that's fine, but can we, for example, test it and then kind of adjust the launch angle as long as it kind of fires the 3 locations automatically?
That's absolutely fine. What I was hoping you were going to say, Dylan, is, or wondering whether you were going to say, is whether you're going to use potentiometers. But if you've got an adjustment, a mechanical adjustment for the angle, and you then want to lock it in place, that's absolutely fine.
Okay, because it's purely mechanical, I was assuming we wouldn't be able to use potentiometers or like SCs. Is that
absolutely
correct?
Right? Yeah.
Okay.
It's just that question tends to come up quite a lot. So, so Sam, have you got that down as a question in a super?
Yeah, I mean, so from what I understand, is basically designing an adjustability for the initial period, so you can tune in the right trajectory. And once it's tuned in, then it will fire the 3 balls, because it has to be automatic. That's my understanding.
Absolutely right. Yeah. That's good. So we've got Daniel Woods next.
Yeah. Could I ask, is there a budget for the prototype?
Yeah. So the question is, what is the group's budget? and we'll put £80.
Okay, thanks.
So from the approved suppliers, you can purchase up to £80 worth of products. And if you also type in there, if you have a separate question, Sam, is VAT included in the budget? And the answer to that is no.
Oh, right, okay.
As a university, we can claim that back, so we won't pass that on to the students. Right, I'm just scrolling down, see if there are any more hands raised.
There's quite a few. There's quite a few technical questions in the chat box about the brief.
Yeah, I was hoping that we're going to get those as questions asked rather than loads of typing.
Lovely. Someone's put their hand up.
Okay, so Yuri.
So just to clarify, so do the 3 balls have to be fired unassisted, or can we put them in like one by one?
Right, so the question there is, must the balls be unloaded automatically, Sam?
Yeah.
Something like that. So all of this is automatic. So what you would do, you would load your launcher up with the 3 balls. And then once you hit or activate the switch for the electric motor, all 3 balls will be launched automatically.
Okay. All right. Thank you very much.
We've got Daniel Thompson again.
Yeah, now that you just mentioned the motor and the switch, if we've got 2 motors, how can we make sure to coordinate them? So if they need to be turned on simultaneously, for example.
Yep, so the question there, if you can capture that, Sam, will be something like, how do we coordinate the motors? I would say run the motors continuously, but if you need to time, say, the second motor, then you can just control the timing from the switch on. See, ultimately, the process will be a continuous process. So let's say we put 12 balls into the hopper or whatever device you've got, then that would repeatedly just, both the motors will be working timed together and would go through all 12 and go through 4 waves so that they would hit each of the zones. So the timing can be, I would say it's best to make it a continuous operation. But if you need to time it by the switch, then you can, that's how you would perhaps ought to do it.
So is that switches in with a manual switch to time the second motor?
Yeah, the switches are manual.
Okay, that kind of seems a bit counter to what we were saying before about all of it being automatic. In my mind. Can you elaborate on that a bit more?
Yeah, so the process is automatic. But if you've got, say, I'm trying to keep this as open as possible because it will be a continuous process. Both the motors will be running, but when you actually want to start the process, might be the feed mechanism, you might choose to do that from one of the switches and not the other. So, for example, you might have one motor for the launch mechanism, but so that could actually be running all the time, and then you might want to start the feed mechanism using a separate motor. So,
okay, but once you flick that, then it all goes on.
Correct.
Yeah, okay.
So I don't know how well you can capture that.
I will write some rough notes and expand them later.
Yeah, so good question. We'll go
Rod, I think some more people need to be let in again.
Okay, thank you, Elise. Yep, just admitting that. And then we'll go to, got a few hands up here, which is good. Let's go to Michael Besant, please.
Hello. Could you explain the line in the brief, the electric motor must not be subjected to any radial or axial loads? What does that actually mean?
Yes. So when you, I'll come back to this next week. So what we'll have is Elise, for this week, it's myself obviously on the Wednesday and Elise on the Friday. And then Elise will have another Q&A on the Monday. And then next Wednesday, I'll be available for sort of general questioning. And I can go through this in more detail. But for now, when you connect the motor to your drive system, there may be issues with alignment. So what I'd like all the groups to think about for the moment is perhaps using something like a coupling or a mechanism that will prevent any radial loads actually working against the output shaft on the motor, so that the motor shaft is turning purely providing torque, pure torque, and not having to overcome sort of frictional effects. But I will go through this again next week. But do ask another question if you want me to. If you've got get me to clarify that even more.
I mean, I've got another question just about the motors.
Okay.
So what do you mean small electric motor? Is that just like a 5-volt brushed motor or what?
Right. So I think your question. So Sam, if you type the question, up to what voltage can we use in our system?
Yeah. And what type of motor? You know, you can get brushed motors, brushless motors, and they need different control systems with.
Right. So what we'll do, we'll come on to that second question, Michael. I'll answer the first one, which I've sort of set up. So the question was, what is the maximum voltage that we can use? And the answer to that is 9 volts. So the type of motor must be DC, and again, because everything else is to be controlled mechanically, you can't have extra control circuits that are going to start to pop and change the sine wave or DC wave going into the motor. So that must what you'll find is if you look on Technobots as a strong guide, you'll see lots of little motors there, some with gearboxes, that will serve you very well for this exercise.
So in regards to the type of motor, does not really matter because you're asking for them to have continuous operation.
Yeah, so these are really DC motors, up to 9 volts. So hopefully that answers your question, Michael?
Yeah, I think so, yeah.
We'll have a think. We'll go to Samuel Graham next then.
How much percent is the manufacturing part of this worth next year?
So the percentages are, so 30% is for your submissions this semester for ME10012. Then next year, the prototype build and presentation is worth 8% of design 3.
Okay, thank you.
We have Zach Dunn next, please.
Hi there. Is there a maximum height that the balls can be fired from?
Is this the height from the launcher?
The height, yeah. Well, the height from the table.
Yeah. So that's right. Let me just. In fact, in the assignment, I've given a working envelope for the whole product. So what I will say is that the launch point should be within the envelope given in the assignment. Maybe plus some, yeah, so, right, so the prototype must fit within that envelope that's stated in the assignment.
You were about to say plus minus. Were you going to give any kind of leeway on that, or are you just going to give that a hard constraint?
Yeah, so right, this will have to be conditional. If you go outside of that envelope, you can do so by, let's say, 150 millimeters, but the machine must collapse into the envelope given in the brief.
And is there any, will they get penalized for breaching that boundary, even if then it can collapse within? Or is that equally as good as a machine which total fits inside that boundary no matter what state of operation?
Right, I'll answer this in another way. When the machine is stored, it must fit within the boundary given in the assignment.
Okay.
But any extension outside of that must be limited to 150 millimeters.
So that'd be a 150 millimeters, I guess, total magnitude, not 150 in X, 150 in Y kind of thing.
Yeah, I suppose we can leave it up to the students because the brief says smaller is preferable. So if you're going outside of that envelope, when it's stored, it has to come back in anyway. You're then adding complications to the design. So
true.
I'm not recommending this at all. But in terms of what we are after, the smaller the design, the better. So that will be in your product design specification somewhere. We got next is Nika.
Yes, sir. I'm just a bit confused because on diagram it's a certain dimensions, and in real life table tennis dimensions are twice as big.
Yeah, this is just a prototype.
Okay, take the dimensions which are in figure 1.
Yeah, this is not the final product that will go to the shops that you'll use on a table tennis table, although the basic mechanism you would just put closer to the net. So one of the questions we had earlier about the net is because this has a curvature, you could still use this on a big table because you just put it a lot closer to the net anyway. So once the balls are fired over the net, then they would get to the player, and the player would then knock them back. But to answer your question, this set of dimensions and this task is not necessarily related to a full table tennis table.
Okay, thank you.
Good spot though.
Let's have a look. Let's go to Charles Cotton. He's got a question. Charles is still there. If you're
nice.
Charles, we can't hear you. You're still muted, Charles.
He said, wait, move on to someone else.
Okay. let's go to Damon Oman then, please.
Hello, so I just had two questions. So the first one was, are we meant to have it so that our machine kind of moves almost like on wheels from A, B, C, or is it meant to fan and stay stationary?
Yeah, so the question will be, must the machine be stationary? And the answer is yes, the machine will be in one position. So the launching mechanism will have to rotate such that it can fire the balls into each of the zones.
And then the next one is, are we meant to have it so that it will fan back and forth so that in a real world scenario, you could fire 20 balls out of this thing or something like that? Or is it only got to do the 3 balls? It doesn't really matter if it returns to the beginning and could repeat the process.
For this exercise, the requirement is to fire just 3 table tennis balls. However, I think better designs would be capable of repeating the wave of 3 balls.
All right, thank you.
Good question. So we'll go to let's go to Michael Bessens.
Hi, I've just seen a couple of good questions in the chat here that I'll just speak out. So someone said, is there a specific time interval for the balls to be fired? Waiting 1 second or 5 seconds between each like ball being fired across the net.
Yeah, good question. So the question will be, what is the cycle time for the 3 balls? And let's make that 18 seconds maximum.
For all 3 balls?
All 3.
Okay. Is there a minimum? Very good question. Rod?
Was that reading that aloud?
Yeah, is there a minimum?
So let's say a minimum of 5 seconds.
And so will you get better marks for doing it quicker? Let's say you did it in 6 seconds compared to 18 seconds. Is there any incentive to do it quicker?
No, it's not about marks. It's just making sure it meets the brief.
Okay.
So we've now got Ivan Chan.
I've got 2 questions. The first one is, can you explain a bit or define the maximum storage volume, like relative to the table, like in which way is the length, size, and width of the machine supposed to be?
Yeah, the volume given is for storage only. The position of your machine must be such that it does not go over the 300 millimeter line, any part of it. So the whole machine must be behind the 300 millimeter line. Then you fire the 3 balls. Then you can collapse it if that's what the machine does, such that it can be stored within the volume given in the brief.
Yeah. Okay. Yeah. So the within 300 millimeters, that constraint. So that doesn't mean that if the prototype being 380 long can like extend beyond the edge of the table.
Yeah, there might, in that case, there would be 80 millimeters, hanging over the side of the table. But the orientation, I think that's your question. The orientation of your machine is completely up to you, but it must be behind the 300 millimeter line when it starts the fire.
Okay,
yeah,
Rod,
okay, thank you.
These guys have got a lecture in like 2 minutes, so maybe just one more question.
Yeah, so let's go to Adam Alatar.
Yeah, I have a question on the assignment brief.
Okay.
In it, you mentioned that the prototype will be judged on the accuracy, its size, and its reliability. I was wondering if you could elaborate more on what you mean by reliability.
Yeah, so this is looking at the mechanism and seeing how well everything works. So what sometimes happens is students will hit the switches, and then things like gears might not be aligned properly, and it might part work, and then after a few rotations it sort of clicks again. So if something's very smooth, all the power goes nicely through all the mechanisms, rotates the shafts, and launches the ball in a very smooth and efficient manner, because all the mechanisms are nicely aligned and are of the appropriate sizes. The shafts aren't flexing and things like that. It's nice and rigid. Then that is what we would deem to be a high quality and more reliable system.
Okay, thank you.
We've got Gautier. It's a question.
And I was just wondering, does the machine have to be necessarily sitting on the table tennis table, or can it be attached to the table at its end?
Yeah, I would say the machine should be placed within that 300 by 750 area. It can be anywhere within there, but it should be placed there.
So we could put it on the edge and have a support holding on the table.
If that all fits within your volume, then I don't mind that. What we're really after is a self-contained unit.
Okay.
That we can just take out of the box, quickly set up, put it on the end of the table, and then flick the switches and off it goes.
So can I just ask, so then is the volume defined relative to the table? Let's say the edge of it defined as the edge of the table, or can that volume just be whatever local to the machine? So technically that volume could go over the edge and they could grab onto it, but that's not really beneficial